In this lecture, we'll see a bunch of formulae called variational formulae for information theoretic quantities, uh, which are sort of a non-standard part of the course. They're not typically covered in this first course, but firstly, I like them very much, so I like to cover them. And secondly, these formulae have in recent years become important for both theoretical as well as practical reasons. Um, so, at a high level, a variational formula for a quantity, say theta, is given by an expression of the form theta equals to max or min over x fx for some function there. And the point here is that there are various ways to view it. One way is to think of this fx for any x as a lower or upper bound on theta. See, because theta is the max or min, so this is a lower or upper bound on theta with and tight lower bound because there is a value for which it matches. That's one way. Second way is to think of these such formulae as providing a method for computing theta as an optimization problem. Okay, so these are two different interpretations. But this is also quite abstract. So in particular, I would like to first start with a variational formula for Pullback-Leibler divergence. Right, so this is our first result. We call it just a lemma. So we are given two distributions. Let's say PMFs, because we can just think of discrete case. So two distributions, P and Q on X, on a finite set X if you want. Okay, such that the support of P is contained in support of Q. So which means that whenever Q of X is 0, P of X is also 0. Then we have dpq equals to max over R, okay, some R. I'll describe which are allowed. Summation over X Px log Rx by Qx. So instead of Px here, you have Rx here. So where this max is over all R, such that the support of R, so R is also a probability measure, and support contains the support of P. Okay, that's what this is. And of course, if R equal to P, then these two are exactly equal. So max is attained for R equal to P. So the max is attained for R equals to P, the PMF R equals to P. Okay, so this is a nice variational formula. It just expresses dpq alternatively in terms of, so instead of having px log px by qx, now you have px log rx by qx. And you can put any r here and that will be less than equal to dpq. But there is one r, specifically r equal to p, for which equality will hold. So firstly, before we discuss this formula further, let's quickly try to write the proof for it, because the proof is in fact quite straightforward. So dpq equals to summation over x px log px by qx. So what we do is we multiply and divide by rx, and this is slightly informal, but you can do it because of this condition. Support of P is in support of R. So if Rx is 0, that's when the division will be invalid. But if Rx is 0, we are fine, because Rx is 0 will imply Px is also 0. So this division will be allowed. Okay. Right. So that's what you can do, and then you continue. Summation over x px log rx by qx plus summation over x px log px by rx. So the second term here, this thing here, is actually divergence between p and r, which is non-negative, and therefore this guy, if you drop this, you will only get you will only get a lower bound for this, because you have dropped something non-negative. And when can equality hold? Well, equality can hold only if this is 0. dpr is 0, which can only happen if p equals to r. And that's the proof. So this is always greater than this with equality if and only if this is 0. Okay, so this is some very simple formula. Okay, now this formula is very simple, but you can build a rich story around this. Okay, firstly, as I said, this gives a family of lower bound on dpq. But let me try to write a different version of this formula, which perhaps which actually has many more applications. So version 2, same formula. Okay, let me use a different color. This one says dpq equals to max over f, some functions f, expected value p of fx, so it's the expected value of f under p, minus log moment generating function, so log moment generating function of fx under q. I'm doing 2 to the power because I'm taking log, otherwise you could have taken ln and done e to the power. Okay, so this one. So how do you prove this form now? So proof is very similar to the previous one, except that you are restricting your family of R to some specific form. So consider this Rx, which was an arbitrary measure, arbitrary probability distribution here, as Qx times 2 to the power fx by, so this is not a probability distribution because this doesn't sum to 1. So how do you make it sum to 1? You divide it by its expected value under Q. So now it will sum to 1. Right, so we consider this, Rx equals to Qx 2 to the power fx by expected value over Q 2 to the power fx. If you sum this guy over x, you will see that the sum comes out to 1 because the numerator also becomes the expected value under Q. So basically we'll repeat the previous proof but with the specific choice of Rx, and this is this can be applied for different f. And note that for f equal to 0, you do get you get Q. Okay. So let's try this one. So dpq once again equals to summation over x px log px by qx, but as before I divide and multiply with Rx, this particular Rx, and then this looks like summation over x px log Rx by qx plus dpr, which is greater than equal to 0. So this guy here is greater than equal to 0 with equality if r equal to p, that's when you'll have equality. Okay, so we'll come back to that condition for equality. We'll come back to it. Okay, but let's continue with this. So this is greater than equal to 0. But R has this nice expression. We can substitute this thing here. So what you get is summation over x px log. Now we'll substitute for Rx. So qx by qx cancel. So it's 2 to the power fx divided by this guy here. So I'll just take it in minus x px log of expected value over q 2 to the power fx. Now this is the constant, so this summation is just 1 here. Okay, so what do you get? This is exactly equal to, and log of 2 is just the function itself, it's exactly equal to the expected value of f under p minus the log moment generating function under q. So this is always, dpq is always greater than this for any f, and therefore dpq must be greater than equal to max over f of this term, because it's greater than equal to for every f, so it must be greater than the maximizing f also. And in fact we can find the f for which equality is attained. Okay, that particular f is where dpr is 0, so equality for, so this is equality in this inequality here, f for rx equals to qx 2 to the power fx by expected value under q of 2 to the power fx equals to px. Okay, so this actually can happen. This can happen. This equality here can happen if and only if log px by qx equals to fx. Let's check this. So if fx is log px by qx, this 2 to the power px by qx is just px by qx. Qx cancels, so this just becomes px. And what about the expected value? This is px by qx, and then what is the expected value of px by qx? That's 1. So this will become px. Okay, so this can happen only when. So this is the choice of f for which equality holds. So there is indeed one f for which equality holds. Okay. Of course, we are restricted to distributions where support of p is within support of q. So you can always find such f. And yeah, for this f equality holds, and otherwise this dpq is always greater than the right side here. Therefore, this is equality where the maximum is attained by max attained by fx equals to log likelihood ratio px by qx. Right? That's the second version. So right, so dpq then is the max of this expected value minus the log moment generating function under q. Okay. So before I proceed now, I think it's important to just remember this formula for the sake of it. It's a very nice formula, and the reason this formula has gained importance, actually there are two reasons. One is, first, it provides an expression for this log moment generating function, which is an important quantity used in Chernoff bound. So this formula has application in statistical physics. I'll elaborate on that link, concentration inequalities, etc. But more recently, this formula has been used to compute dpq. So this expresses dpq as a maximization over f, and therefore if you can complete this maximization, you can compute dpq. However, in practice, since this maximization is over any function f, this is difficult to do. So what people do is they replace this maximization with a computational proxy, which is just some heuristic argument with some max over functions f from some family. For instance, family of deep neural networks. This is roughly the idea used in implementation of so-called GANs, generative adversarial networks. This maximization is relaxed to some maximization of a class of functions coming out of a deep neural network. Okay. So these are the two formulas, which two variational formula for dpq. They are roughly identical. In fact, these formula are not so new. They go back quite a few years. Okay, let me try to see if I can get both of them. So these two formulae here, this one and then this one. So these two formulae, they relate to rather classic formulae, some which have been rediscovered several times under different names, starting with the Laplace integration formula of Laplace. So it goes back to Laplace, and then the Gibbs variational principle in statistical physics. Variational principle, that's also related to these formulae. And then most recently perhaps the Donskar Varadhan formula. You can look these things up online. All these three different formulae which have been discovered at different times, apart by 100 years or more, uh, they can be related to the formula that we have been seeing, except that instead of expressing divergence in terms of this quantity, we will express this quantity in terms of divergence. So this quantity is quite important. It's the log moment generating function, and it's used in Chernoff bounds. So suppose that you have a random variable x which is zero mean under q, and we would like to express the log moment. We would like to we will find a variational formula for log moment generating function of such a zero mean random variable x. So the log moment generating function, instead of using log to the base 2, it's customary to use the natural log. So ln of expected value of e to the power lambda x. This function as a function of lambda is called the log moment generating function. And what we can show is that this guy is equal to max over q, that soup over q, soup over p. So you take all PMS P which are which have their support contained in Q. Okay, that's a technical condition. I'm just skipping that. And now you just need to take expected value of this guy under P instead of this log moment generating function, which is log of expected value. This sort of linearizes this function minus a correction term, and that correction term, interestingly, is dpq. Okay, so this formula, which is very similar to the one here, is called the Gibbs variational principle. Okay, so instead of divergence, I have this thing on this side, and this is a very useful formula, comes up in many places, and it's related to this formula. So indeed, this formula is not new. Okay, now that I have pointed connection of our variational formula to Gibbs variational principle, and I would like to discuss this one a bit more. So one way to view our variational formula is that it's an expression, a variational expression for this distance. Now this is a distance not between the two PMFs P and Q, but this distance is not the usual Euclidean distance that we're used to. It's some other distance. However, what we will see is that, I'll give you some heuristic interpretation of this part, that this formula actually has a corresponding counterpart in the Euclidean geometry as well, the geometry which we are more familiar with. So we'll get a counterpart of this formula in Euclidean geometry. I'll discuss that. And what you can view is that this formula is the corresponding formula in the information geometry. Okay, we'll call this information geometry. So what is Euclidean? What is that counterpart? It is the Cauchy-Schwarz inequality, and I'll discuss that next. Okay, so let's come to this very vanilla Euclidean geometry world. Okay, so can you write a variational formula for the Euclidean distance square? dpq in your head should be thought of as a proxy for Euclidean distance square. I've mentioned this before as well. Okay, so let's see. So suppose x and y are two d-dimensional vectors. So here is x, this is y. Then can you write a nice variational formula for x minus y square, which is similar to our variational formula for total variation for Pullback divergence, which I'll just write here so that you remember that formula. This one says dpq is equal to max over r summation over xpx log rx by qx. Okay, here is the formula. You may or may not have seen it. Okay, this one says this is but you can easily derive it. This is max over all z, another z in Rd, another d-dimensional vector, just like we added a distribution R here. Norm of x minus z square plus, this is my third point that I've introduced for this formula, plus 2 times the inner product between x minus z and z minus y. So this one is saying that the x minus y square, take any z, take this distance, take its distance square, add to it 2 times this inner product. So what is this? So x minus z is, sorry, I should keep, yeah, this should be fine, I guess. Yeah, this is correct. So x minus z is this vector. Sorry, x minus z is this vector, and z minus y is this vector. So this inner product is this guy is equal to 2 times x minus z, the length of this vector, z minus y, the length of this vector, and cos theta, which is the angle between these two vectors. So angle between these two vectors. Okay. Yeah. So what's the angle between these two vectors? So if you have the first vector is like this, the second vector is like this. This is the angle theta here. Sorry, this diagram, the direction turned out to be a little bit bad, but you understand what is the angle between these two vectors. Okay, so that's cos theta. All right. So this is some quantity which looks strange, but this is equal to this. How do we show this? Very simple. We follow the same proof as this one. We add and subtract this z, and then expand. So what happens is square plus second distance square plus 2 times the angle between these two vectors, the inner product of these two vectors. And since this guy is non-negative, I can always drop this guy. So this is greater than equal to x minus z square plus 2 inner product x minus z square, inner product x minus z minus y. And this holds for every z. Therefore, you can put this also hold for the maximizing one. And which is the maximizing z? Well, that's z equal to y, because that's the only way this guy is 0. So when z equals to y, this guy is 0 and this becomes x minus y square. So this is also a variational formula for x minus y square, the Euclidean distance square. And this formula, basically its corresponding thing in the information geometry world. So what is this information geometry world? Now these vectors are not in Rd. These vectors are distributions. So this is the probability simplex, the set of all possible distributions, let's say of finite dimension, because the alphabet is of finite size. So P and Q are 2 elements here. And this proof, actually, if you examine it carefully, is very similar to the other proof where we chose another R and had some notion of distance from P to R, R to P, and so on and so forth. Except that, unlike the Euclidean world, where we have angles between vector and some nice physical interpretation of that angle, there are no, it's not clear what is the notion of an angle in this DPQ world, okay? And therefore, this formula somehow provides some interpretation of that angle part. This is very high level thing, but you should draw parallel with this formula in information geometry versus a formula in Euclidean geometry, such as this one. Okay, this is first. Now, there's another very nice formula in Euclidean geometry which we use all the time, which actually if you don't use it, then you're not doing enough maths. And that's basically the Cauchy-Schwarz inequality. So what does the Cauchy-Schwarz inequality say? It says that if you have two vectors x and y in Rd, then the inner product between x and y, Okay, you should just think of, okay, this, I've never defined it, I'm assuming that you are familiar with this guy, but let me just write it here. This is the summation I equal to 1 to, it's the angle, if you divide it by, maybe I should define angle. So how do you define angle between x and y? So the cosine of angle between x and y is this guy, okay, where xy is summation I equal to 1 to d xi y I. Right, and the Cauchy-Schwarz inequality says that this thing is between -1 and 1. Okay, so in other words, mod xy, or let's say xy square, is less than equal to norm x square norm y square. This is the Cauchy-Schwarz inequality. Let me put a box. Very important inequality, used left, right and center. Hölder's inequality is a generalization of this one. Now, can we view this inequality geometrically? Yes, indeed. So what this inequality says is, take a vector y and take some vector x here, and let's look at a line passing through this x. So this is all vectors which are lambda times x. So the claim is that any vector on this line must be at a positive distance from y. You agree? This is obvious, right? So for all lambda in R, lambda x minus y is greater than equal to 0, and therefore also for the closest point here, the closest point to y, which is just min over lambda, this guy is greater than equal to 0. Alright, so what is the minimizing lambda? In fact, you can find the minimizing lambda here. So let's expand this guy here, this lambda x minus y square. This is norm of the first vector square, lambda square norm x square. Norm of the second vector square, norm is just the length, minus 2 times lambda xy. So you want to minimize this guy over lambda. You can do that just by differentiating. The minimum is attained by lambda star equal to 2 lambda norm x square equals to 2 xy. I'm just differentiating and setting a derivative to 0. So the minimum is attained by xy in a product divided by norm x2 square. Okay. So this implies the minimum over lambda, this thing here, is equal to, I'll substitute this lambda, this is equal to norm xy square. Okay, so I put a mod just so that we know concretely what's going on, and then by x2 square, but one x2 square cancels, so it's just x2 square plus norm y square minus 2 into norm xy again square by norm x2 square. So this is exactly equal to norm y square minus mod x minus y square by norm x square, and this guy is non-negative because, well, this is just the minimum of non-negative numbers, must be non-negative, and this implies, this is the Cauchy-Schwarz inequality. So this is if and only if norm x square norm y square is greater than equal to xy square. Okay, so yeah, okay, so we derived the Cauchy-Schwarz inequality. Why are we deriving the Cauchy-Schwarz inequality? The interesting thing here is that if you look at this alternative expression for dpq, this implies that you can view it as an inequality, that this dpq is more than this right side for any f. So this sort of implies that dpq plus log q to the power fx So yeah, we just derived the Cauchy-Schwarz inequality. I'm just trying to tell you why we derived the Cauchy-Schwarz inequality. So this guy here is greater than equal to expected value of EPF. This is an implication of this inequality here. In fact, I would like to argue that this is the Cauchy-Schwarz inequality. This is actually exactly the Cauchy-Schwarz inequality of the information geometry world. So how do we see that? Okay, so let's try to see that. So let's quickly try to mimic the proof of Cauchy-Schwarz inequality. So I'll just call it the Cauchy-Schwarz inequality of the information geometry world. So what happens now? Now we have a distribution P, okay, and there is a distribution Q. Actually, perhaps it's better to restrict to a smaller class. This is true for any function f, but we can also substitute fx equals to lambda x here. Okay, this is just a specific function. In this case, dpq plus the log moment generating function is greater than equal to lambda times expected value over p of x. Okay, so that's what we are trying to. Sorry, let me just backtrack. Yeah, so this guy here is for this particular function, this inequality is the same as dpq plus log moment generating function is greater than EP of lambda x. Okay, right, and so as I was saying, this is actually, this particular case is the Cauchy-Schwarz inequality for the information geometry world. Okay, so how is this the Cauchy-Schwarz inequality of the information geometry world? So we had this distribution P and this distribution Q. This is inside the probability simplex set of this. The probability simplex is the set of all PMFs on this finite set X. So we drew this line through X here. Now the corresponding line in this world would be this line through. I'm just making a line through P, and an arbitrary member on this line is P lambda, given by P lambda of x. Just like we had lambda x, this P lambda of x. This is slightly different from a line. It is this guy. You can check that for every lambda, this guy is a PMF, and therefore it's this kind of line. This is actually called, this is basically an exponential family, so-called an exponential family passing through P. And now, just like we wrote here, the distance here is non-negative. Similarly, the divergence between this Q and P lambda is greater than equal to 0 for every lambda. This implies, if you expand this, summation over x qx log qx by P lambda x is greater than equal to 0. Now P lambda x has px times this, so we will basically expand each and every term. First term is P lambda x is px, so this first term is dqp. This is the first term here corresponding to p. The second term is corresponding to this guy, so that's just log, because this is just a constant, it's log of ep e lambda x. And then the third term here is just this guy. So this is minus lambda expected value over q of x, and this is greater than equal to 0. So yeah, okay, so we got a role of P and Q interchange, but we got the inequality, the Cauchy-Schwarz inequality of the divergence world is exactly the same as what we got from our variational formula for dpq. This is greater than equal to this plus log okay. So yeah, so these formula, the ones we saw here, which leads to these kind of inequalities, for instance this one here, these are basically sort of the Cauchy-Schwarz inequalities for the information geometry world, and that's what we have been deriving. Okay, so in summary, we have this variational formula for Pullback-Leibler divergence, which is sort of elementary to derive, but has connection to many interesting formulae. For instance, Gibbs variational formula, Laplace integration formula, Donskoy-Varadhan formula, and this is sort of we could draw parallels of this formula with the corresponding inequalities in the Euclidean geometry world. However, in the Euclidean geometry, instead of dpq, we use a square of distance here. Okay, so dpq is roughly the counterpart of square of Euclidean distances. Okay, that's what I want to bring out in this part. Okay, so now let's move on and try to derive another variational formula for another quantity, the mutual information. Right, so the main result now is the following. You have a discrete distribution P on X and a channel W from X to Y, describing the conditional distribution. Then for this discrete distribution in this channel, we know that we can write the mutual information in terms of both divergence and entropy. That's something we've already seen. It's a divergence between the joint distribution between x, y and the product of marginals. But there's a very interesting, again, geometric interpretation of the same formula. It's a variational formula for mutual information. This is minimum over all Q, where Q is the PMF on Y, the output alphabet. Okay, minimum over all Q of summation over X, Px, the input distribution, divergence between Wx, the distribution on the output when the input is X, and Q. So what is this formula? You can view it as follows. So your channel has all these distributions, W1, W2, blah blah blah, as many distribution as the size of the alphabet X. Okay, Wx. So there are a lot of distributions here, and you fix some distribution Q and take the distances, this divergences between Wx and Q. And take the average with respect to Px. So each of them is weighted with Px. Find the Q which minimizes this distance, the average distance. Okay, it's sort of the centroid when you weight by this Px. Okay, so in that context, this mutual information somehow gets related to how spread out these distributions are, where weights are fixed according to P. Right, so it gives a nice geometric meaning to mutual information. Okay, so how do we show this? Do we show this particular formula? So the proof is actually very simple, although the interpretation is very nice, but the proof is very simple. So this mutual information between P and W is summation over X Px. This is just a formula for mutual information. Wy given X log Wy given X, W of P, the output distribution Y. That's what mutual information is. Now what I'll do is I'll divide and multiply this with Qx, some output distribution Qy. And so this first part here, this one here, will be taken out as one sum, and the second part another sum. Okay, so the first part here is equal to summation over x px. Now what do you have here? Summation over y wy given x log wy given x by qy. This is exactly the divergence between qx and wx and q. It's the first part. What about the remaining part? That remaining part is summation over x px, summation over y wy given x log of qy by wp of y. Actually, there is no x in this part here, so you can take this summation over x inside, and so this guy you can take it inside, and when you sum it over x here, what you get is that this term here is exactly equal to wp of y. So this whole thing here, yeah, so this whole thing here, as I said, you can express this as w of p of y. So this whole thing here is, the first term is summation over x px, the divergence between wx and q. That's what the term we want to retain, and this whole thing here is minus d of w of p, the output distribution when the input distribution is p, and q, and this is non-negative. Therefore, you are subtracting something from this, therefore something positive. Therefore, IPW is always less than this term here. So it's always less than this term here because it's something smaller than this. But there is a choice of Q, which is Q equals to W of P, for which equality holds here. So IPW will be equal to this if and only if Q equals to W of P. Otherwise, IPW is smaller than this. Therefore, IPW is the minimum of this quantity over all Q. Sorry, I wrote max here. This should be min. Right? So that's the proof. Okay. Right. So it's the Q which minimizes the average distance, sort of the centroid, but the averaging is with respect to Px. That's what IPW is. Okay. In fact, this particular formula here can be very useful, okay, to get further upper bounds in Fano's further lower bounds for a probability of error in Fano's inequality, and get an alternative expression for so-called the capacity of a channel. Okay, so we will cover that in the next video. In the next video, what I'll do is I'll cover various applications of these formulae that we have derived. All right, so see you in the next video.